You ever look at a complex machine, like really look at it, and wonder how it all works? From the incredible force of a pair of pliers to the giant sweeping arm of an excavator, there's this hidden, almost simple elegance behind it all. And it turns out a lot of that mechanical magic comes down to one single, super simple rule. See, mechanisms are everywhere. They're kind of like the skeletons of our machines, right? Just these rigid parts, we call them links, all connected by joints. And their whole job is to take one kind of motion and turn it into something else, usually multiplying force while they're at it. Just look at these vice grips. You squeeze the handles, and this whole system of interconnected bars converts that little bit of hand movement into this crazy powerful clamping force. It's a perfect example of what we call a planar mechanism, where everything moves on flat, parallel planes. Now, let's scale that way up to something like an excavator. That whole arm, with its massive range of motion, it's all controlled by a series of these linkages. The position of that bucket isn't some kind of magic. It all boils down to pure geometry. And at the heart of so many of these systems is one fundamental building block. So let's break this down to its simplest possible form. We're going to focus on the most basic closed-loop linkage you can make, the 4-bar linkage. Honestly, this thing is the absolute cornerstone of mechanical design. If you understand this, you can understand almost anything that follows. It looks simple, right? And it is. Just 4 rigid bars, or links, connected by 4 joints to make a loop. That's the whole thing. But the variety of motion you can get from this simple setup is just incredible. And every single bit of it, comes down to the lengths of these 4 bars. Okay, before we dive deeper, let's get our vocabulary straight so we're all on the same page. The one link that's fixed and doesn't move, that's our base. The 2 links hooked up directly to the base are the turning links. And that last one, the one that connects the turning links and kind of floats in the middle, that's the coupler. Easy enough? So here it is, the big question. How can we just look at a 4-bar linkage and, just by knowing the lengths of its bars, predict exactly what kind of motion it can make? Well, this is where a beautifully simple rule called Grashof's condition comes into play. It's kind of the secret key to all of this. This is the one question that Grashof's condition answers. Can any of the links in this system make a full continuous 360-degree rotation? A link that can do that is called a crank. One that can only swing back and forth is a rocker. And the answer to this question basically determines the entire function of the machine. And here it is. This is the secret code. A simple little inequality that tells you everything you need to know. It just says the length of the shortest link plus the length of the longest link has to be less than the sum of the other 2 links. That's it. So let's put some labels on these. We'll call the shortest link S, the longest one L, and the other 2 are P and Q. Doesn't matter which is which. To figure out how this thing is going to move, all you have to do is plug those 4 lengths into that simple formula we just saw. All right, so now that we have this rule, we can use it to analyze any 4-bar linkage and figure out what kind of motion it's going to produce. This is what we call the analysis part. You take a design that already exists and figure out exactly what it does. This condition creates a really clear dividing line. If the inequality holds true, if S plus L is less than P plus Q, we've got ourselves a Grashof linkage. That means at least one of its links can spin all the way around. If it's false, we have a non-Grashof linkage, where absolutely nothing can make a full circle. So here's our first type of Grashof linkage. If the shortest link, our S, is one of the turning links, you get what's called a crank rocker. That shortest link becomes the crank, spinning in a full circle, and it drives the other turning link to just rock back and forth. This is perfect for taking a motor's rotation and turning it into an oscillating motion. But what if you get clever and make the shortest link the base itself, the fixed part? Well, then you get a double crank, or a drag link. Now both of the turning links attached to that short little base can spin a full 360 degrees. You get 2 cranks for the price of 1. So what happens when the math doesn't work out? What if S plus L is actually greater than P plus Q? Well, then you get a non-Grashof linkage. In this case, no link can spin all the way around. Both turning links can only rock back and forth, which is why we often call this a double rocker mechanism. The whole thing is limited to just oscillating. Okay, this is where things get really powerful. Because instead of just looking at a mechanism that exists, we can flip this whole thing around and use the rule to design a machine that does exactly what we want it to do. This is called synthesis.
Let's try a classic problem. You need to design a windshield wiper. You've got a motor that spins and spins, but you need the wiper blade to just sweep back and forth in an arc. So how do you turn that continuous rotation into a nice steady oscillation?
We can just follow the logic step by step. Our goal is rotation into oscillation. Well, that's the literal definition of a crank rocker. So we know we need a Grashof linkage. All we have to do is pick 4 numbers for our link lengths that satisfy the rule, where S plus L is less than P plus Q. Then we just make that shortest link our crank, hook it up to the motor and the base, and boom, we've just designed a working windshield wiper system from scratch.
So let's just pull back for a second and think about what this really means. This isn't just some abstract math equation, it's a whole new lens you can use to look at the world of machines around you.
To sum it all up, it's pretty simple. The entire motion of a 4-bar linkage is predictable from that one little inequality. If it's a Grashof linkage, you get full rotation, and the specific type, crank rocker, double crank, just depends on where you put that shortest link. And if it's non-Grashof, nothing spins. Everything just rocks back and forth.
But hey, don't just take my word for it. The absolute best way to really get a feel for this is to play with it yourself. There are some fantastic simulators online, little web apps, where you can just punch in different lengths for S, L, P, and Q, and they'll animate the whole thing for you. Test the condition, make a prediction, and then see if the animation proves you right.
Seriously, once you see this pattern, you can't unsee it. You'll start noticing it everywhere. The suspension in your car, the arm on a desk lamp, a pump jack in an oil field. The logic of the 4-bar linkage is behind so many things. So the next time you see something moving, take a closer look. You might just be able to figure out its secret with one simple rule.